Welcome to my YouTube channel. I'll be talking about resolution of vectors in this topic, how to resolve a given vector into two perpendicular components. And this topic is a follow-up, a continuation of the topic, scalars and vectors. And my previous video lessons, I've taken time to explain what a vector quantity is. A quantity that has both magnitude, that is size, and direction. An example is displacement, velocity, acceleration, force, and so on. Now, we've already shown you again how to represent a vector, that you can use a segment of a line having an arrow attached to it to represent a vector quantity both in magnitude and direction. And today we are looking at the resolution of vectors. You see, resolution is a reverse process. It is the splitting or breaking down of a vector into a number of components, and each component acts in a particular direction. The component of a vector in a given direction is the effective value of that vector acting along that direction. And three perpendicular directions are always recognized. They are the x-axis, and any component acting along that direction is called the x-component or the horizontal component. We also have the vertical component, and then we have the z component. But in this lesson, I'm going to be talking about resolving a vector into two perpendicular components. And what are they? The x component, which is the horizontal component, and the y component, which is the vertical component. And any given vector can be resolved in a similar fashion. You can resolve a force vector, a displacement vector, and acceleration vector into any two perpendicular directions. The x direction, which is horizontal, and the y direction, which is vertical. Now, given this vector f acting along this line OA, let's say from point O, that is the tail of the vector, and then the tip of the vector, which is point O. Now, this f is a symbol for the vector, representing the vector both in magnitude and direction. And let's say that we can place a line here along the x direction, such that the angle the vector makes with the x direction is theta. This is my x direction. I want to resolve this vector f into its two perpendicular components. I want to find the components of the vector acting along the x direction and along the y direction. So what I'll do is to draw my axis x and y. Maybe I'll place my y axis also, just like I've done for this. So I need to first of all draw the two perpendicular axes, the y axis and the x axis. And then I'm going to drop a perpendicular from the head of the vector to meet the OX line at point B, such that this makes angle 90 degrees with the OX line. Then if possible, I'll drop another line, or draw another line from the tip of the vector to the y-axis at right angles to it. So what I need to find is the component of this vector, one, acting along this x direction, and the second component, that's the vertical component, acting along the y direction. Okay, so if I refer to, because this triangle OAB is a right angled triangle, it's a right angled triangle, and then I make reference to my SOHCAHTOA. Okay, my side here, theta, that is the direction of the vector, is given by the opposite side, which is AB, over the hypotenuse, which is vector f. Now what I need is the magnitude of the resultant vector f. This symbol represents the vector f both in magnitude and direction. So we use this symbol to represent the modulus of f, which also means the absolute value of f, the magnitude only of vector f. Okay, so I'll now cross multiply this over 1. If I cross multiply, I have AB equals modulus f, which is the magnitude of f, sine theta 1. I can say let AB be equal to FY. So FY component is acting along this line. And since this line is equal to this line, it therefore means that the component of F acting vertically is still the same thing as the Fy. So whatever I have here, using this equation, is the same thing as the length of this line. So that gives me Fy is equal to F sine theta. Similarly, I have, if I use cos theta now, my cosine theta is the adjacent side, which is OB, over the hypotenuse, which is F modulus. So that my side OB, my OB now is equal to F modulus as absolute value of F cos theta. Now come back here. My OB, I can call that Fx. That is the component of vector F that is acting along the x-axis. So since OB equals Fx, I can replace my OB with Fx. So that gives me Fx is equal to F modulus cos theta. So with this equation and this other one, I can have the two different components of vector F. And the two components are acting at right angles to each other.